Imagine if your everyday objects could literally talk to you, not with words, but with color. What if a material could show you it's been stretched too far, maybe? Or that a package has been opened without you even touching it?
It sounds pretty futuristic, right? But today we're taking a deep dive into, well, the rather technical-sounding mechanochromic palettes of cholesteric liquid crystal elastomers for visual signaling.
Okay, that's a mouthful.
It is. But basically, we're talking about these incredibly smart materials. They use, really noticeable color shifts to visually signal mechanical changes. So things like stretching or being compressed or even bent.
Right. So our mission for this deep dive is to really get under the hood, understand how these materials work, what makes them tick, and maybe most importantly, what kind of exciting real-world applications they could enable for you, the listener. So let's start right at the beginning. What exactly is mechanochromism?
Okay, yeah. At its core, mechanochromism is just a material's ability to change color when some kind of mechanical force is applied to it. Think of it as the material visually, well, speaking about the stress it's under.
Okay, that makes sense. Stress equals color change. So how do these specific materials, these cholesteric liquid crystal elastomers, how do they pull that off?
Yeah, so it comes down to combining two key players, really. First, you've got cholesteric liquid crystals. We call them CLCs. Now, these aren't like your typical pigments, like in paint. They actually have this unique helical structure. Think like a tiny, tiny spiral staircase at the molecular level.
A spiral.
Exactly. Right. And this structure reflects light in a very specific way. It creates what we call structural color. The crucial part is that the color you actually see depends entirely on the pitch of that helix.
The pitch?
Yeah, the pitch. It's the precise distance it takes for the molecules to twist around a full 360 degrees. Change the pitch, you change the color.
Interesting. Okay, so that's part one. With the second part?
The second component is elastomers. Now, these are probably more familiar. They're soft, really flexible polymers, things that are super stretchy, but then, importantly, they spring right back to their original shape, like a very high-tech rubber band, basically.
Yeah, right. Okay. Stretchiness and bounce back.
Exactly. So when you cleverly combine these CLCs with elastomers, you get CLCEs. Cholesteric liquid crystal elastomers. And these materials, they beautifully blend that mechanical flexibility from the elastomer with the optical responsiveness of the liquid crystals.
Ah, so the stretchiness meets the color-changing spirals.
Precisely. And here's where it gets really neat. When you apply mechanical force, like stretching to a CLCE, you physically deform that delicate helical structure within it. That deformation subtly changes the pitch or maybe the orientation of those tiny spirals, and that change is what triggers the visible color shift you see.
Wow.
And what's really quite groundbreaking here is the precision. You're not just getting some vague random color shift. It can be engineered to be a calibrated visual signal.
So the physical deformation directly translates into a specific visual signal. That's incredibly elegant. I'm curious now, what actually goes into making these? What's the sort of recipe for a CLCE?
Right, the ingredients. Well, to build these CLCEs, you need a few key things. You start with the liquid crystal monomers themselves. These are the basic building blocks that have that liquid crystal property. Then, critically, you add special chiral dopants. These are like the molecular architects. They're the ones that actually force the liquid crystals to arrange themselves into that specific helical, that spiral shape.
To make the spirals happen.
Exactly. And they even control how tightly round that spiral is the pitch, which, as we said, directly sets the reflected color. Then you need cross-linking agents. These are molecules that link the polymer chains together to form the stretchy, rubber-like network of the elastomer.
Ah, the rubber band part.
Yes. And the density of this network, how many links there are, actually affects how sensitive the material is to force. This whole structure is usually built within some kind of flexible polymer backbone or matrix, which provides the overall mechanical support. Think of it like the scaffolding.
Okay.
And finally, you need initiators. Usually photoinitiators triggered by light, or sometimes thermal ones. They're just needed to kickstart the chemical reactions, the polymerization that locks everything together.
Okay, so it's quite a specific mix of ingredients to get this effect. We understand the chemistry, kind of. But for us, for the listener, so what? Where might we actually see these materials making a difference? What are the visual signaling applications?
Yeah, good question. The applications are actually quite compelling, I think. Imagine wearable strain sensors, maybe integrated into smart clothing or even medical bandages. The color could immediately tell you how much a joint is bending, or perhaps how a wound dressing is stretching as it heals.
Direct visual feedback.
Exactly. Or think about smart packaging or labels. You could have a CLCE label on, say, temperature-sensitive medication or food. It might subtly shift color if it's been exposed to improper temperatures.
So like a warning sign built right in?
Precisely. A clear, immediate visual warning before you even open it. No ambiguity. And in fields like soft robotics, these materials could be amazing. They could provide crucial real-time visual feedback. Maybe a soft robotic gripper visually indicates the pressure it's applying just by its color.
Okay, that's clever.
And one more anti-counterfeiting. You could design materials where unique color patterns appear only when you touch or press them in a specific way. A dynamic, very hard to copy authentication feature.
Right, for proving something's genuine.
Yeah, so what's really powerful here is that these mechanochromic palettes, using CLCEs, they offer this incredibly versatile platform. By carefully engineering the internal structure, that helical pitch, and the elastomer network, we can really fine-tune their optical response to different kinds of mechanical forces. It opens up, well, almost endless possibilities for materials that visually communicate with us in real time.
That really is a powerful thought. Imagine a world where your everyday objects could actually talk back to you visually about their condition or status. A shoe that changes color to show where it's wearing thin, maybe. Or, like you said, a package that instantly reveals tampering with just a glance. Makes you wonder, what else could these smart materials visually communicate in our world?